Hello, my dear students. Welcome to IK Sir Chemistry classes. Here we are in lecture number 7 on the chapter Electron Transfer Reactions. In this video, we are going to discuss self-electron exchange reactions and cross reactions. So far, in this chapter, we have learned electron transfer reactions by outer sphere mechanism and inner sphere mechanism. But the electron transfer reactions by outer sphere mechanism are of two types. And the first one is electron self exchange reactions. The electron transfer reactions in which the reactants and the products are identical is called an electron self-exchange reaction. Let us see it again. There are some electron transfer reactions in which the reactants and the products are identical, and such electron transfer reactions are called electron self-exchange reaction. The oxidant and the reductant of such electron transfer reactions are complexes of the same ligands with the same metal but in different oxidation states. It means the oxidant and the reductant of electron self-exchange reactions contain the same ligands and the same metal, but the oxidation state of metal are different in them. The velocity constant of two electron self-exchange reactions are denoted by K11 and K22. Here K is small. A few examples of electron self-exchange reactions are given below. FeCN whole 6 4 minus having leveled iron atom reacts with FeCN whole 6 triple minus, forming FeCN whole 6 3 minus with leveled iron atom and FeCN whole 6 4 minus. It is an example of electron self-exchange reaction. The oxidant and reductant, this is oxidant and it is reductant of such electron exchange reaction, electron self-exchange reaction are of similar type. They have same ligands and the same metal, but the oxidation state of metal is different. Here the oxidation state of iron is +3 and the oxidation state of iron is +2 here. In electron self-exchange reactions, the reactants and the products are identical except the leveling of iron atom. There is another example, FeH2O whole 6 2 plus having leveled iron atom reacts with FeH2O whole 6 triple plus, forming FeH2O whole 6 triple plus with leveled iron atom and FeH2O whole 6 2 plus. The oxidant and the reductant in this case also contain the same ligands and the same metal but in different oxidation states. The reactants and the products are identical in this case also except the leveling of iron atom. CO bipyridyl whole 3 2 plus with leveled cobalt atom reacts with CO bipyridyl triple 3 times triple plus, forming CO bipyridyl 3 times 3 plus with leveled cobalt atom and CO bipyridyl whole 3 2 plus. This is also an example of electron self-exchange reaction, and it is another example of electron self-exchange reaction. Here the ligand is tripyridyl, which is a tridentate chelating ligand. Here BIPY is bipyridyl while TERPY is tripyridyl. These are some examples of electron self-exchange reactions in which the oxidant and the reductant contain the same ligands and the same metal but in different oxidation states. At the same time, the products and the reactants of such electron transfer reactions are identical. Let us see structures of bipyridyl and tripyridyl. This is bipyridyl, which contains two donor nitrogen atoms. It is a bidentate chelating ligand, while tridentate contains three donor nitrogen atoms, and hence it is a tridentate chelating ligand. Let us see now second type of electron transfer reaction by outer sphere mechanism, and it is cross reaction. The electron transfer reaction by outer sphere mechanism in which the oxidant of one electron self-exchange reaction and the reductant of another electron self-exchange reaction are involved is called a cross reaction. Let us see it again. The electron transfer reaction by outer sphere mechanism in which oxidant of one electron self-exchange reaction and the reductant of another electron self-exchange reaction are involved is called a cross reaction. The reactant and the product of such electron transfer reactions are different and they may have different ligands also. Let us see an illustrative example of cross reaction. Let us consider two electron self-exchange reactions as follows. This one is electron self-exchange reaction number 1 with velocity constant K11, and this is another electron self-exchange reaction with velocity constant K22. Let us now consider an electron transfer reaction by outer sphere mechanism taking place between the oxidant of reaction number 1. This is the oxidant of reaction number 1, which is taken here, CO bipyridyl 3 times 3 plus, and the reductant of reaction number 2, reductant of electron self-exchange reaction 2. This one is the reductant of electron self-exchange reaction 2, and it has been taken here. The oxidant of electron self-reaction 1 and the reductant of electron self-exchange reaction 2 are taken in this electron transfer reaction by outer sphere mechanism, and therefore it is an example of cross reaction, and its velocity constant has been represented by K12. Here, this labeled cobalt atom is oxidized from +2 oxidation state to +3, while the oxidant having normal cobalt atom is reduced from +3 oxidation state to +2. This is an electron transfer reaction by outer sphere mechanism, and it is an example of cross reaction. Here, the reaction 3 is called the cross reaction of electron self exchange reactions 1 and 2. The reaction number 3, which was given at the end of last slide, is nothing but the cross reaction of electron self exchange reactions 1 and 2. Its velocity constant is denoted by K12, and this velocity constant is given by a simplified version of the Marcus equation as follows. K12, this is the velocity constant for cross reaction, and it is equal to under root K11 multiplied by K22 multiplied by capital K12 and multiplied by F12. This is equation number 4, and the terms involved in this equation 4 are discussed on the next slide. Equation 4 is called Marcus cross relation or cross equation. Equation 4 is called Marcus cross relation or cross equation. Here K11 is velocity constant for electron self exchange reaction number 1, and K22 is the velocity constant for the electron self exchange reaction number 2. K12 is the velocity constant for the cross reaction number 3, and capital K12 is nothing but the equilibrium constant for the cross reaction number 3. And the term F12 is given by this relationship. Log F12 is equal to log K12, that is the equilibrium constant for the cross reaction, square divided by 4 log K11 K22 divided by Z square. And let us see the terms involved in this equation number 5. Here Z is the number of collisions per second between the oxidant and reductant in the solution. Z is the number of collisions between the oxidant and the reductant per second in the solution, and its value is approximately equal to 10 to the power 11 liter per mole per second. In the present case, the values of different terms at 25 degrees centigrade are as follows. The value of K11, that is velocity constant for electron self exchange reaction number 1, is 9 liter per mole per second. Please note that the reaction is of second order, and hence the unit of velocity constant is liter per mole per second. The velocity constant for electron self exchange reaction 2 is 48 liter per mole per second, and the equilibrium constant for the cross reaction is 3.57, and all these values have been calculated experimentally. Accordingly, the value of F12 can be calculated from equation 5 as follows. We have already seen that log F12 is given by this relationship. Let us put the values in this equation number. In this equation, log F2, the value of capital K12 is 3.57. The value of K1 is 9 liter per mole per second. The value of K22 is 48 liter per mole per second, and the value of Z is 10 to the power 11, and its square will be 10 to the power 22. On solving it, we have log F12 is equal to this term. This is the value of log 3.57 and its square, and on solving this term, 9 into 48 into 10 to the power 22 will be equal to 4.32 into 10 to the power minus 21. And log F12 will be equal to, its square will be 0.3058 divided by 4 into the value of log of this term is equal to, this is the log of 4.32, 0.6355 minus 21, and on solving these two terms we have 20.3645 and with negative sign, and finally the value of log F12 we calculate minus 0.00375, and accordingly F12 will be anti-log minus 0.00375, and on solving it we have F12 equals to 0.99. Please try to take anti-log of this term with the help of log table and submit your answer in the classroom. Therefore, the velocity constant for the cross reaction can be calculated as follows. We have seen that the velocity constant for the cross reaction, that is K12, is equal to under root K11 into K22 into capital K12 into F12. Let us put the values of these terms in this equation. It is 9 liter per mole per second. It is 48 liter per mole per second. The value of equilibrium constant is 3.57, and the value of F12 we have already calculated, and it is equal to 0.99. And on solving it, on multiplying this term, this term, this term, and this term, we get under K12 is equal to under root 1526.81, and the square root of these two terms will be equal to liter per mole per second, and the square root of this term is equal to 39. That is, the velocity constant for the cross reaction is 39 liter per mole per second, and this value has been calculated with the help of experimental values. The value of K12 for the cross reaction calculated with the help of Marcus cross relation is reasonably in close agreement with the experimental value, which is 64 liter per mole per second. The experimental value of velocity constant for the cross reaction 3 under consideration has been found to be 64 liter per mole per second. But the value of velocity constant for this reaction calculated with the help of Marcus modified equation, Marcus cross relation, Marcus cross equation has been found to be 39 liter per mole per second, and these two values are not widely different. These are in close agreement, and therefore the Marcus cross equation or Marcus modified equation for the cross reaction works reasonably well during the calculation of velocity constant. Thank you for watching the video with concentration. Please like and share it. And if you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.